I've always wondered how humans were able to discover the shape of Earth's orbit around the Sun. Sure, you may think of observing through a telescope, but it's really hard to tell just by seeing, because they appear to be very circular. And even with modern telescopes, it's not that easy. But let's do something fascinating. What if we could tell the shape of the orbit just by doing physics and math? In this video, we are going to solve for the path of any planet that revolves around a fixed star. But before anything else, we first need to study the possible shapes or paths taken by the two bodies. If you've studied conics, you know that there are 4 possible shapes. When you cut a cone, at different possible angles you see that there are 4 distinct types of shapes: a circle, an ellipse, a parabola, and a hyperbola. In mathematics, we have generalized these plotted shapes into equations. You can either write them in Cartesian or polar coordinates. But in this video, we are going to focus on the polar coordinates because it's way easier to solve equations. You don't need to know everything, but here E is the eccentricity and D is the distance from the directrix. These determine what the shape is going to be. Keep this exact fractional form logged into your memory because it's going to be the finish line of our derivation. First, let's make sure that all of us are on the same page. Force vector by which bodies attract is given by F vector equals minus gm m over r squared in the r hat direction. By Newton's second law, F equals ma, we can write that a vector equals minus gm over r squared in the r hat direction. From here, to see how we obtain a differential equation, we can write the acceleration vector in its polar coordinates. Now we have 2 sets of differential equations. First, let's solve this second differential equation because if you observe using chain rule for product of functions, you can rewrite this as the rate of change of r squared theta dot. And it just means that the rate is equal to 0. Now what does that imply? By now you probably realize that this term must be a constant, so let's name it h. But the real implication is that it's just angular momentum in disguise. We know that L equals mrv, or mr squared theta dot. It's clear from here that the differential equation we just solved shows that the angular momentum is constant throughout. To make the expression less messier, the term gm is going to appear a lot often, so we name it mu. Let's come back to our first differential equation. Now, we can happily substitute theta dot equals h over r squared in it. To simplify this equation even further, we do a substitution, let u equals 1 over r. But before that, we want to end up with a solution in terms of r and theta only. So, the time variable should be eliminated somehow. And would you look at that? We have a simplified expression for r dot. Similarly, we can find r double dot too. After the substitutions, we have arrived at the most simplified differential equation. Many of you might have seen an equation of this form. Harmonic oscillations like mass spring systems, LC circuits, and simple pendulum also have the same equation describing its motion. A cleaner way would be to understand that such differential equations mostly involve a cosine or a sine. To take into account for both the sine and cosine, we can predict that our final solution would be made of a constant plus another constant times cosine of theta but shifted by theta naught. And would you look at that? We directly have the relation between r and theta. But something even crazier is that it highly resembles our generalized conic equation in polar coordinates. By now we clearly see what dictates the shape of the orbit of the planet around the star is based on these constants. we can directly compare and find out the constants c and theta naught. This is why not all orbits are elliptical, because based on the factors like the initial velocity, initial distance between the planets, mass, and even the energy, the path of the planet changes. For a perfect circular orbit, we need the eccentricity to be 0. And in the real universe, it's practically impossible to have a perfectly circular orbit. But an elliptic one? Sure. For a bounded system, the energy is negative, and by accounting some other factors, we can clearly see how eccentricity has possible values between 0 and 1. And if you wanted a body to be slingshotted, it's going to have an eccentricity greater than 1, meaning the energy has to be positive. But how exactly do total energy and initial velocity mathematically map to this eccentricity constant E? That is a story for the next video. If you ask me, it's really fascinating, and the first time I ever got to know, when I was a kid, that the Earth's orbit is elliptic, I didn't even think of it much, because like you, even I just accepted it. But now, here we are, deriving the path taken by heavenly bodies. It's truly amazing, and that satisfaction we get, it's immense, I know. There is a lot more we can cover, but we have answered our primary question. Now we can rest knowing that our orbit around the Sun is elliptic. If you're interested, we'll later talk about the laws of Kepler in later videos. Thank you for watching, see you in the next video.